Welcome back. We are proving certain theorems about Kummer extensions. These are extensions which adjoin an nth root to a field that already contains an primitive nth root of unity. And so far we have proved that a Kummer extension is a cyclic extension, meaning a Galois extension whose Galois group is cyclic. And today we are going to prove that a cyclic extension is a Kummer extension. So if F is a field containing a primitive nth root of unity and you have a cyclic extension of degree equal to n, then K is the splitting field of an irreducible polynomial of the form x power n minus a, which is to say that it is a Kummer extension. So we just started the proof last time, so let me continue now. So let's say G is the Galois group of that extension and zeta is a primitive nth root of unity in F. So since G is n, order of G is n and G is cyclic, we do know that there is a generator of which will be of course of order n. So let us take sigma in G, a generator of G. Then we have 1 sigma, sigma square, sigma power n minus 1 are all distinct F automorphisms of K. In fact, they are all the automorphisms of K, F automorphisms of K, because G is exactly those powers of sigma. So now way back we proved that any collection of distinct characters is independent. So by our earlier results on characters, independence of characters, so we are going to use that now. We have used this of course to set up Galois theory. Now we are going to use this directly again. By our earlier results on independence of characters, 1 sigma up to sigma power n minus 1 are independent as functions from K to K, independent over F, right? So that means in particular 1 plus zeta sigma, zeta square, sigma square is not identically 0 as a function on K, right? Because zeta, independence means no non-trivial linear combination is 0. So zeta of course is, you take 1 times 1, zeta times sigma and so on. So this is clearly a non-zero function. That means there exists a non-zero element beta in K such that this function applied to beta is non-zero. So alpha, which is defined to be alpha beta, 1 of beta is beta because beta is the identity function. Sorry, 1 is the identity function. Zeta sigma beta, zeta square sigma squared beta, zeta n minus 1 sigma power n minus 1 beta is alpha is non-zero, right? So it's not an identically zero function. That means on some element in the domain it is non-zero. So take a beta on which it is non-zero and let's call the image alpha. So alpha is a non-zero element of K. So alpha is a non-zero element of K. Now let's apply sigma to alpha. Then we are going to get a bunch of equations like this. So let's apply sigma to alpha. Sigma is a homomorphism, right? So and zeta is fixed by sigma. So I'm going to write sigma square beta because sigma of sigma beta is sigma square beta plus zeta square sigma cubed beta all the way up to zeta n minus 1 sigma power n beta. But what is sigma power n? So I'm going to write that here. Sigma power n is identity, right? Because sigma is the generator of this group which has order n. So this implies sigma alpha is sigma beta plus sigma square beta, zeta square sigma cubed beta all the way up to zeta n minus 1 beta, correct? Because that's sigma n is beta. sigma n beta is beta. So now continuing this further, what we get is, and also note that zeta is a order n element also. So zeta power n minus 1 is another name for zeta inverse. This is because zeta n is identity. So zeta n minus 1, zeta is 1. That means zeta inverse is zeta n minus 1. Correct? Because zeta n minus 1 times zeta is 1 means zeta n minus 1 is the inverse of zeta. So we can rewrite this as zeta inverse beta. So now I am going to skip a step here. So sigma alpha is equal to zeta inverse times zeta sigma beta, zeta square sigma square beta, zeta cubed sigma cubed beta. The previous term will be zeta n minus, so maybe I will write that here. The previous term here is n minus 2 sigma n minus 1 beta plus zeta n minus 1 beta. That was the previous term. So now I am factoring out a zeta inverse. So this will become zeta n minus 1 sigma n minus 1 beta plus beta, right? Zeta n minus 1 is just a scalar, right, because it is in the base field. So I am pulling that out. So you factor zeta inverse out. So zeta inverse, which is of course zeta power n minus 1 out. So you get here, of course there is nothing, so it will be zeta inverse zeta. So there must be, you have to increase the exponent of zeta at its place. So zeta here, zeta square here, zeta cubed here, zeta n minus 1 here, and zeta power n here, that is 1. Okay. So but this, if you just stare at this, is so let's see, what is this? This first term is beta, I mean I put that here. This is exactly equal to alpha, because beta plus zeta sigma beta, zeta square sigma square beta, zeta cubed sigma cubed beta, zeta n minus 1 sigma n minus 1 beta. So this beta, if you put here, this is exactly like alpha. So this concludes the proof that sigma alpha is zeta inverse alpha. This is going to be used by us in a minute. Okay. So this is a pure calculation, right? So there is nothing deep here, and I hope the calculation is clear to you. So sigma alpha is zeta inverse alpha. Now we are going to claim that, remember our goal is to prove that K over F is a Kummer extension. That means K must be obtained by adding an nth root. I claim that alpha itself is that nth root, which is to say alpha power n is in F. And the proof is clear. It's a one-line proof. So the proof is that sigma of alpha power n is of course sigma alpha power n. This is because sigma is an automorphism. But sigma alpha power n is zeta inverse alpha power n, right? Because sigma alpha is zeta inverse alpha. But zeta inverse is an nth root of unity. So zeta inverse power n is 1. So this is just alpha power n. This means sigma alpha n is alpha n. This means alpha n. So this of course implies that sigma power I of alpha power n is alpha power n for all I. So alpha power n is in the fixed field. So alpha power n is in the fixed field of G, because every element of G which is of the form G is exactly 1 sigma sigma square sigma n minus 1. Each of them fixes alpha. So alpha power each of them fixes alpha power n. So sigma power n is in Kg, but Kg is of course F. This is because K over F is Galois. So Kg is F. So that means alpha power n is in F. So that proves the claim. So now we are going to take, let A be alpha power n which is in F. So then the first point is K is the splitting field of, right, and the reason for that is clear, because roots of x power n minus a in K are alpha, zeta square alpha, zeta n minus 1 alpha. So and k is generated by them. K of course is so remember what is the alpha that we have. Yeah, so I'm going to prove this in a minute, but actually I think we should prove that F alpha is the splitting field. So maybe I should write that here. F alpha is the splitting field of x power n minus a. This is the first statement. This is easy, of course. And okay, so this, let me prove this carefully. So F alpha is the splitting field of x power n minus a. This is because x power n minus a splits completely over F alpha. This is because all the n roots of x power n minus a are in F alpha. Namely, what are the n roots? Alpha is one of them, because alpha power n equals a, which is alpha power n, right? Then zeta alpha power n is also a. Zeta square alpha power n is a. Similarly, zeta power n minus 1 alpha power n is a. This implies the roots are alpha, zeta square alpha, all the way up to zeta n minus 1 alpha. There are n minus 1 of them, n of them. So all the roots are there, it splits completely, and of course F alpha is generated by alpha over F. So F alpha is a splitting field, right? Now we claim, second statement is that F, which is x power n minus a, is irreducible over F. Second statement is this, and then that will tie up everything. So why is this irreducible? And the reason is the following. So note that sigma alpha is that I have showed earlier. So sigma alpha is zeta inverse alpha. So sigma, this is what we have, and then this tells me that sigma square alpha, so maybe I'll write it here. So sigma square alpha is sigma square or sigma of sigma of alpha, which is zeta inverse alpha, which is zeta inverse sigma alpha, which is zeta inverse alpha, so that is zeta power minus 2 alpha. So similarly, sigma power I alpha is for all I, right? So sigma I alpha is that. Now sigma power, so our situation is this: k is an extension of F alpha, and that's an extension of F. So sigma I is a automorphism of k, and it sends alpha to sigma I sends alpha to zeta power minus I alpha, which is in F. So that means, which is in F alpha. So each sigma I restricts to an automorphism of F alpha, right? Because its image is contained again in F alpha. So this implies sigma I of F alpha is contained in F alpha. Because once alpha has image in F alpha, capital F of course is fixed. So every polynomial in alpha with F coefficients, its image under sigma power I is again in F alpha. So it restricts an automorphism. Once it's contained in this, because F alpha is an algebraic extension, image is F alpha. So it is an automorphism of F alpha. So, and moreover, sigma I is not equal to sigma j for I not equal to j. Indeed, suppose sigma I of alpha is sigma g of alpha. If they are identical automorphisms of F alpha, that means they agree on alpha. But that means because sigma I alpha is zeta power minus I alpha and sigma j alpha is zeta power minus j alpha, this implies, okay, and here of course we are only taking I between I greater than equal to 0 but strictly less than n. But if zeta power minus I is equal to zeta power minus j, this will guarantee that I equal to j. Okay, so this is the proof of this. If I and j are different, sigma power I cannot be equal to sigma power j. I mean, this is another way of saying that sigma has order n as automorphism of k, but because alpha separates powers of sigmas, they are distinct as automorphisms of f alpha also. So hence, we are almost done now. The Galois group of f alpha over f has at least n elements, right? Because each sigma power I, so the point is each sigma power I is in the Galois group of f alpha over f. So that is the first statement here, because it restricts to an automorphism. And the second statement is that they are all distinct. So there are at least n automorphisms in the Galois group of f alpha over f. But this is equal to f alpha f if you want, because this is a Galois extension, right? Because it is a splitting field of a separable polynomial. I mean, it is splitting field of this polynomial which is separable by characteristic assumption. But this is less than or equal to k colon f, because f alpha is an intermediate field. So this degree is less than this degree. But this is, of course, n is by hypothesis. So that is part of the hypothesis, and hence everything here is 1 equal. So f alpha colon f is equal to n. This means f alpha is equal to f. And this further implies that, f alpha is k. So that's the statement that x power n is irreducible. Because if it is not irreducible, then the degree of f over alpha over capital F, degree of alpha over capital F, which is the degree, which is the extension of the extension degree, is less than or equal to n, because alpha satisfies, and if this is equal to n, so basically if this is equal to n is what we have just shown, and f alpha is 0, okay, so I'm sort of messing this up a little bit, but f alpha is 0, f is of course x power n minus a. Then f alpha is 0, degree f is n, and degree of the irreducible polynomial of alpha over f is n. So that means f is the irreducible polynomial of alpha over capital F. That means this is irreducible. So this completes the proof that, so let's go back to the original statement of theorem 2. If you are given a cyclic extension, we did prove that k is the splitting field of an irreducible polynomial, this we just showed, over the base field, which is to say cyclic implies Kummer, Kummer implies cyclic, and hence this theorem is proved, the theorem, main theorem, which is to say Kummer if and only if cyclic. So this is really saying that Kummer if and only if cyclic. Okay, so let me, I have a few minutes left in this class, so let me just tie up some loose ends and prove, or at least start studying something which will help us when we talk about solving polynomials by radicals. Okay, so let me just give you a preview of what we are going to do later. Let k over f be, okay, so let's say f is a field, and let's say k is some extension of f, and alpha is in f. Okay, so we'll come back and give these definitions formally later, but I wanted to use Kummer extensions that we just studied so that this will be fresh in your mind to indicate what we will do later. So we say that alpha is expressible by radicals over f if there exists a tower of field extensions, let's say f, which is f0, then f1, finally fr. So in our usual way, this is fr minus 1, f2, f1, f0, which is f, such that a couple of things happen. One is that alpha is in fr. So this k that I started with is irrelevant for this. K is just given so that we need to talk about some elements that are in an extension field. So otherwise k is not important. And 2, each extension fi over fi minus 1 is a radical extension. That is, fi equals fi minus 1 alpha I with so radical extension is one where it is obtained by adding a radical. So basically what we are saying is that this is f0 alpha 1 and a power of alpha 1. Alpha 1 is an n1th root of f. So f2 will be, okay, so maybe I'll just squeeze that here. f1 alpha 2, where alpha 2 power n2 is in f1 and so on. So all the way like that. So and this will be fr minus 1 alpha r, where alpha rth power will be in the previous field. So if you recall from the beginning, first class in fact, in that language alpha can be expressed as an function, as using elements of f and addition, subtraction, multiplication, division and radicals. So that means taking roots, right? Because alpha is in fr, so it can be written as a polynomial with fr minus 1 coefficients with polynomial in alpha r, but alpha r is a root of something in fr minus 1. So it becomes obviously very messy, but in principle you can do that. For example, as a simple example, let's say you have q contained in q root 2, cube root of 5. Okay, so here anything here can be expressed as in terms of radicals and in rational functions. For example, cube root of 5. So any element of this can be expressed using, of course, the usual operations, but radicals. Okay, so the point is, you take this, I mean any function element here will be something, some root 2 a plus root 2 b root 2 plus c times cube root of 5 plus d times cube root of 5 whole square plus e times root 2 times cube root of 5. I mean it can be something complicated. I do not care how complicated it is, but it can be done is the point. So the Galois theorem is used to show that roots of a quintic polynomial cannot be expressed like this. Is the main achievement of Galois theorem is that there is a quintic polynomial whose roots cannot be expressed by radicals. That means you cannot construct a tower of fields like this. Okay, let me quickly tell you how to connect this to Kummer extensions. If f contains a primitive nth root of unity, then a radical extension is merely or simply a Kummer extension. So this is the important thing. So remember, radical extension, this is the crucial property that that we are seeking in solvability of quintics, and Kummer extensions are like that, except that you need to have a primitive nth root of unity and a suitable radical extension, not any radical extension, but a radical extension where you only adjoin nth roots. And Kummer, if and only if cyclic, assuming that f contains a primitive nth root. So this, basically what I am really saying is that this is in the realm of solving polynomials by radicals. This is something that mathematicians were trying to do 200 years before Galois. So this is, brute force expressions of roots. So think of Kummer extensions. Actually think of, so maybe I'll write down radical extensions if and only if Kummer extensions, equivalent to Kummer extensions, equivalent to cyclic extensions. So this is our theorem today, and this is if f contains primitive nth roots. So this is not in general true, but this is in the realm of solving polynomials by radicals as in Galois time. Right? And this is of course the same thing. So this is like this, because if f contains primitive nth roots, but most of the time it will not, right? Because Galois was interested in solving polynomials over Q, which will not contain. We will know how to address that later. So this is same as this. But this is not doing by brute force, but this is, is in the realm of group theory. So this is much more conceptual and amenable to systematic study. So this is much more amenable to systematic study. So now the point of Galois really is, he translated the problem of messy formulas for roots which existed for cubics and quartics, and of course quadratic formula also. And people were trying to see whether such a formula existed for quintics. That becomes very messy, and if you search online for Cardano's formula for cubics and similar formulas for quartics, they become extremely messy, and in fact you don't know how to use them. And it was just hopeless to see if such a thing existed for quintics using such methods. Galois really translated the whole problem into a much more systematic conceptual problem using group theory, and this is the crucial bridge. We converted Kummer extensions to cyclic extensions, and hence the theorem, today's theorem, or the theorem of the last 2-3 videos, is hence very important for us. It allows us to compare radical extensions to cyclic extensions. And modulo this simple, this slight worry that we have, that Kummer extensions are not just radical, but radical extensions where the base field contains primitive nth roots of unity, but that we will easily solve that problem. So basically we will see later that f is any extension, any field, and k is an extension field, and alpha is in k. Alpha is expressible by radicals over f if and only if, so the definition is this, where basically there is a tower. So this means, so I'll write it here. So this condition 1, and I'll write condition 2 here. But condition 1 is really saying that there is a tower like this. Such that alpha is in the last one, such that each of them is a simple radical extension, meaning it is obtained by taking an nth root. As I said, that's messy and it's not easy to deal with such definition. Whereas the second condition is there is a tower fields, let's say f equals f0 prime, f1 prime, fk prime or fm prime, such that alpha is in fm prime and each fi prime over fi minus 1 prime is a cyclic extension. So basically this is condition 1 and this is condition 2. And the condition 2 says this very complicated looking tower is replaced by a very beautiful, simple and conceptual tower where the last one contains alpha as always, but this is nothing, I mean it's not messy like what is a radical extension, but it's simply a cyclic extension. So now it's not clear at all in this world, any information about the group that you have can say nothing about whether such a tower exists or not. Whereas the group, any such tower has very strong restrictions on the group, because for example if you take the Galois group of the extension fm prime over f, there is something called a composition series, or there is a chain of subgroups, right? Because this is a cyclic subgroup of G such that the quotient has such an expression. So this is related to the notion of solvable groups. So what I am trying to say here, this is just an indication of what is to come. This is the traditional notion of solving by radicals. Okay, so this is the traditional notion. Galois converted this into a group theoretic problem. Okay, this is the contribution of Galois, and then you can argue all of this we will do later. Basically you can argue that S5 is not solvable and hence it cannot, any polynomial degree 5 polynomial, he constructed certain degree 5 polynomials whose roots, if they can be solved by radicals, then there is a corresponding picture like this, which would imply that S5 is solvable, but it is not. Okay, so this is the crucial theorem that makes it work, and this is a crucial theorem which connects Galois theory, which basically connects classical problem of solving by radicals into groups, a problem in group theory, and this is all of this I am saying it today because it is connected to Kummer extensions. So this will be used, Kummer extensions will be used when we prove this. If F contains, the final remark, let me, I am taken too much of your time already, but final remark I will make is that if F contains primitive roots of unity. I will not say which primitive nth roots for various n. Okay, may not, I mean, because it depends on what are degrees of these. If f contains primitive nth roots of unity, this equivalence, this already basically follows from our theorem on Kummer extensions. So that is what I want to end today with. Basically, if f contains primitive nth roots of unity, then radical extensions are really nothing but Kummer extensions, and Kummer extensions are cyclic. So you can just take the same thing at each stage. This is Kummer, so this is cyclic. But f may not contain primitive nth roots of unity. In fact, the most interesting case for us is when f is q, which will not contain primitive nth roots of unity except when n is 1 and 2. So we will need to figure out what to do with that, but that's a simple trick that will solve that problem, and that is the place where we have to deal with cyclotomic extensions, which we are going to do in the next video. So next video, next 1 or 2 videos we will do cyclotomic extensions, and after that we will get to the business of the course, which is to show that quintic polynomials cannot be solved by radicals in general. Okay, so let me stop today here, and then we will continue with cyclotomic extensions in the next class. Thank you.